Hello, today we're looking at volume by cross-sectional area, one of our applications of integration. And in particular we're looking at what's called the disk and the washer method. So as we're going through here it'll be apparent why we use those names for the techniques we're going to use. But here we're going to use these integrals to find some volumes. Okay, so up till now we've only used integrals to find areas. Now we're actually going to look at volumes. Okay, so we'll leap straight into our theorem. Okay, so we have a solid, and we're going to orient it along the x-axis, and we're going to assume that each little cross-sectional area has area AX, and then we can integrate that A of x from A to B to find that volume. Okay, so it's taking lots of little pieces and adding them together to find a volume, and we'll take an example of that. So suppose we want to find the volume of a pyramid. Okay, it's a nice simple shape. We'll assume it has a square base, and each side of the square base is 10 inches, and we'll assume that the height of the pyramid is 5 inches. Okay, well, I think at the start we'll think about what this looks like. Now note there's a couple of ways to think how we orient the pyramid compared to our axes. We'll have it here. I think this is easiest, although there are other ways of doing it. We'll have the point centered at the origin. So the pyramid, the base is actually sort of coming out of the origin there. And it's heading along the x-axis, so you can see from our graph here the x-axis is sort of going straight down through the middle of it. We have the base 10 and its height is 5, which again we can see on the diagram here. Because the length of each side is 10 and the height is 5 at the base there, we know that at any point, we'll call it x, along the x-axis, the base of this little square is twice the x value that we're at. So right here, if we're at the point x, the square we have has side 2x by 2x. Okay, and that's going to be important as we find these areas. Okay, so that's the area. Let's think about this in terms of volume. And what we're doing, we're taking a typical kind of slice through this pyramid. Okay, we take a square and then we give it an extra dimension. We make it three-dimensional. So the way to think about these things, they're kind of little, I guess, really very flat cuboids. An easier perhaps way to think about it, if you think about the slices of cheese you can get. Okay, they're square but very thin. That's essentially what this is here. Okay, so this particular one, it's at, I guess, x equals 3. So we can think about the side here. The side will be 6 by 6. But the height of the cuboid, where you have a three-dimensional thing, is now delta x. So in general, if we have one of these slices, it's 2x by 2x, and it's going to be delta x width. Because it's a cuboid is very easy to find the volume of. We just take the width times length times height. So of course that would be 2x multiplied by 2x multiplied by delta x. Okay, so if we think about this and leap in, if we want to find the total volume of the pyramid, we take each of these slices. Remember they were 2x by 2x, so in other words 2x squared by delta x. That's the volume of each of these little slices. And if we sum all those slices together, we approximately get the volume of the pyramid. But of course, to make it perfect, and we've seen this many times already, to get that perfect, we want to take the limit as n goes to infinity. Okay, we take infinitely many slices, it gets a better and better approximation, and as we take infinitely many, it's actually perfect. So if the limit as n goes to infinity, if I equals 1 to n, and then this is the volume of each of those slices. And again, hopefully this little piece here is familiar. These are the Riemann sums we've seen, and this becomes an integral. Okay, so that limit of the sum of the delta x, it just becomes the integral. Now the integrand, the piece inside here, remember we had 2x and then squared it, so it's of course just 4x squared. And the limits go from 0 to 5, because if you remember, the pyramid itself went from x equals 0 to x equals 5. So this is the integral. This is the integral setup for the volume of our pyramid. And hopefully you can see that once we got to this stage, this is trivial. This is very easy. Use the power rule, so we add 1 to the power, divide by the new power. So we get 4/3 x cubed between 5 and 0. Plugging in the 5 and the 0, we get about 500 over 3, and that's inches cubed. Those are our units, if you recall. The units were inches, which is 166.67 inches cubed. So that's the volume of that pyramid. Okay, so that's a specific example. We're now going to kind of generalize a type that we can see that we can integrate over and over, and this is the disk method. So disk, think of it as being like a compact disk or some sort of very thin disk you might find. And we're going to take some sort of function y equals f of x from a to b, and we're going to rotate that around a horizontal axis, and we're going to let Rx be the radius of the cross-sectional disk at x. Okay, and well, we're finding the area of a circle. We know if we have a radius of r, then the area of a circle is pi r squared. And all this integral is doing is taking each of those little disks and summing them together, just as we saw with the pyramid, to get an integral which gives us the total volume. Okay, so the volume of our solid is pi, and the pi we're just taking outside the integral. It's fine. And then we integrate from a to b, and we have rx squared, the radius squared dx. Okay, so in the abstract this looks a little difficult, but we should maybe try an example and see how we do. Okay, so for example, let's take the function y equals 1 over x, and we're going to rotate that around the x-axis from x equals 1 to x equals 2 and find the volume of that. Now in all these cases I recommend, if at all possible, you draw a diagram. Even if it's just a two-dimensional diagram, it'll help you see kind of what's going on. Because I have a computer here, I can take a 3D diagram. Okay, so x just goes from 1 to 2, and our function is 1 over x. So there's our function, the blue line there, from 1 to 2, and that's what we're going to rotate around the x-axis. And then you can see the red disk here, that's just a typical disk that we've got. Okay, so its radius is 1 over x, and therefore its area, the area of that two-dimensional disk, will be pi multiplied by 1 over x quantity squared. And then of course we wish to assign it a width. It's got a very thin width of delta x. So with that cross section, and we'll just have a little look at the diagram of the whole thing, that's what our solid's going to look like. Again, we've got the red disk, which is just some sort of typical disk in there, but the whole thing is, I don't know, kind of the nose of a plane a little bit. Not quite. Anyway, so there's our shape. So again, we take this sort of typical disk, it's pi 1 over xi squared delta x, that's the volume of one little piece, and then we take the limit of the sum, and of course that becomes an integral again. Again, because it's from x equals 1 to 2, we're in the integral from 1 to 2, and we get 1 over x squared dx, and we still have that pi outside. It's always good to remember that. Kind of easy to forget to include that pi, but we're talking about circles and the pi r squared, so the pi should be there. Okay, and again, the integral itself is not hard. We can square out that. Again, I use the power rule. This is x to the negative 2. So we add 1 to the power, divide by the new power, it becomes negative x to the negative 1, or minus 1 over x. And that's from 1 to 2. Plugging in the 2, we get negative a half. Plugging in the 1, we get minus 1. So this comes to pi over 2. We didn't actually have units in this case, so it's just units cubed. So that would be the volume of that solid rotated around the x-axis. We just look at the picture again. There it is. That has pi over 2 units cubed volume. Okay. One more thing. So we mentioned we were going to do the disk and the washer method. The washer method is very similar, and in fact maybe we'll just bring in here a picture of a washer just to see what we mean. Okay, it's a disk with a hole in it. Okay, that's basically what a washer is. So because it's a disk with a hole in it, we have two radii now. We have the outside radius, which here we've denoted with uppercase Rx, and the inside radius, lowercase rx. And this is very similar. The volume now is simply the uppercase Rx squared minus the lowercase rx squared. We integrate that from a to b. Again, because of the previous example, this isn't too hard. Just a quick reminder, the one thing that throws people a little bit, we square before we subtract. Somehow it's tempting to subtract the radii and then square, but you can see here we square then subtract, not the other way around. And this will give us the volume of that solid. Okay, so let's take another example. So we're going to find the volume formed by rotating the region bounded by y equals x squared minus 2x plus 2 and y equals 2x minus 1 around the x-axis again. Again, if you recall from areas between the curve, when we say bounded by, it's probably some sort of region that's enclosed. And we'll see in a second that that's the case. Okay, so let's take a look at this again. And first of all, maybe we'll start by looking at a two-dimensional version of this. Okay, so here are our two functions. So the blue line is the 2x minus 1. and the red line is the x squared minus 2x plus 2. And so that's just a little 2D shape. You can see that the 2x minus 1 is higher, so that'll be the outside radius when we're rotating around the x-axis. And that's what it looks like in 2D. Okay, so now we've got a more complicated diagram. Let's think about what this looks like in 3D. Okay, so you can see over here we have the two-dimensional drawing just like we had before. These are our two functions. And we're going from 1 to 3 because that's where these things are constrained. That's where the two functions meet. And that's a good point. To find those two values, you just set the two functions equal to each other. And you can see a sort of a little thin piece on the left here going up from left to right at this point. But now we can also look at the 3D version. Okay, so we come over here in the 3D version. Again, we have the two functions here and here. And here, hopefully, you get an idea of what the washer looks like in each case. Okay, it's constrained by this outside radius and inside radius. And as we move this along, they're both getting larger, but they meet up again here. And then as we go down, the radius comes down, getting bigger and bigger until eventually the washer sort of squinches back up on itself. And we look at it from sort of end on. Again, you can see, here we go, so we've got our washer appearing, and as it gets bigger and bigger, eventually it'll disappear again as the two lines meet. There and there. Okay, so that's kind of what the shape we have. Now let's try and sort of build this. Okay, so as it's traveling along, let's see what shape this actually makes. So what we're doing here is tracing the two radii as we go along. Just try and see what shape it makes. Okay, so the outer, the blue here, made kind of a cone with a hole in the middle, and the inner red is making kind of also a cone but curvy. So if we look at the shape it's creating here, that's kind of pretty. Hopefully you get an idea for the shape. It's kind of a big loudspeaker, I guess. Okay, there's the shape we're getting. Look at it from this side. Look at it from this side. Okay, so we certainly don't need this graphic necessarily to see what it becomes. But I do think it's nice to have a sort of a graphical interpretation of what's happening here. Okay, so back to the question. Okay, so we saw the 2x minus 1 with the outer, the x squared minus 2x plus 2 was going to be the inner, and let's just remind ourselves of our formula here. And with this formula in mind, I think this isn't too bad. So we integrate, we have the pi outside, we integrate from 1 to 3, remember that was where the two functions met. And then we have the outer, the 2x minus 1 squared, minus the inner, the x squared minus 2x plus 2 squared. And again, the integral itself is not bad. We square everything out and put like terms together. We actually form the integral, like so. It's not all that hard. And plug the values in. And again, we get about 104 over 15 pi, or 21.78. Okay, so that's the disk and the washer method. As I say, the formulas are fairly straightforward. I do recommend always, if you can, to draw a picture before you start integrating. Even if it's just a 2D picture to give you an idea of what's going on. Okay, and that's about it.